Screencast and everything.
Literally doesn't make sense.
The original derivative.
Yeah, think about this. So we talked about the fact that the antiderivative or,
It's like a double negative.
oh, if I could spell antiderivative though.
Derivative.
There we go. Remember, when you hear the word integrals, you evaluate the integral by finding the antiderivative. Okay, so when we think integral and we think antiderivative, you should be thinking the same thing. And that is working backwards. And we learned some of these shortcuts yesterday. Yeah, remember the power rule? Okay, so you get your original function. Now that's the indefinite integral. So what we're going to look at today, if you look down here, these are again our definite integrals, which means they have bounds. So that means all of these have an actual answer. You have a number answer. It's not some weird formula with that plus c at the end. You can actually evaluate these. And again, what does the integral represent?
The area under the curve.
The area under the antiderivative, but it's the area under the curve. That is what we're actually representing. So we're going to be able to today, using our shortcuts, be able to figure out the exact area under the curve without graphing it. Okay? So no graphing. Now we do have a way to check on our calculator. That's fine. You could check with your calculator. But I haven't shown you that method yet. Or did I? Did I show you how to check with the Math 9?
Yeah.
I think I did.
Well, math we used before.
Okay.
Just to find it. I don't think it was to.
Math 9. Okay, but let's look at the formula first. This is kind of a little proof of what we're going to evaluate here, but for right now, because I know it's difficult to understand, I'm just going to kind of show you the formula so you get used to using this formula, and we'll evaluate them. And then the next class is actually our fundamental theorem of calculus. That's where we formally define it.
Chain rule.
Chain rule doesn't come till next chapter.
Yes.
Okay, so basically what we're going to do is we are going to integrate this function. So notice I used a lowercase f. Another way to think of this would be the antiderivative of the derivative. You get back your original function. So you get back this f of x, whatever that might be. Sorry, that should be a t. Let me just switch this. Let me just switch this to a t. What's that?
It's like ln and e. They cancel, right?
Exactly. So if I take the antiderivative of the derivative, I get back the original function. So when there are bounds here, basically we want to evaluate this from a, our lower bound, to x. So in order to do that, we plug in the top and then we subtract the bottom. So that's our result, and that is something that we can evaluate. Again, I'm going to talk more about the theory behind it next class, so for right now, just kind of go with it and say, all right, this is what we have to do. And so that's what we're going to practice today. So when we want to evaluate the antiderivative of the sine of x from 0 to pi, we don't have a way to do this. If you actually think of sine is, right, like this. So here's pi, but this isn't even like a semicircle. So we couldn't even use areas if we wanted to. We could approximate using our Riemann sums, right? The Riemann, the RRAM and LRAM. But so far, the only way we can actually figure this out would be if we used our calculator. But now, what's the antiderivative for sine? We learned these yesterday. It's negative cosine. Remember, if you have to look back, you can look back. So I want to evaluate this. So we put our evaluation line, but we have a lower 0 and an upper is pi. And so that's going to be, And this is where we have to like remember our unit circle and stuff like that. So we have negative cosine of pi minus, and then negative cosine of 0. So cosine is the x coordinate, so it's going to be the opposite.
Negative 1.
Yeah, it's negative 1
Positive 1. So it's 1. It's 2.
minus negative 1. So it becomes 1 plus 1? 2. Now think about the significance of that. I mean, I think it's kind of neat, but the area under the curve from 0 to pi is 2. Exact, okay? Because we're saying integrals are limits, so the exact area under that curve is equal to 2. So what's going to be from pi to 2 pi?
Negative 2.
It would be negative 2, and if you wanted to find the area that's bounded, it would be 4. Yeah. Yeah, the whole thing would be 0 because it would cancel it out. But if I was asking for the entire area that was bounded.
Right.
Okay, next one. So we want to integrate 3x squared. So remember, we add 1 to the exponent and we divide by that new exponent. So it becomes 3x cubed over 3. So it's just x cubed, evaluated from 1 to 2. So we have 2 cubed minus negative 1 cubed. So that gives us 8 plus 1, 9. So again, imagine what we're saying is here's this 3x squared. If I wanted to find the area under the graph from 1 to 2, I can now find out that has an actual area of 9. And we're not using any kind of formulas other than knowing those integration rules. It's very cool, right? Because you think about, like, there's no way to find the area under that. Well, there is, and that's the purpose of our integrals, our antiderivatives. So now you can say I can find the area. Basically, you can find the area under any polynomial. You can find the area under e. You can find the area under sine or cosine or secant squared. Now, there's some other rules we haven't learned yet, but those are the basics. Don't forget with negative exponents, rules still apply, right? So it's negative x to the negative 1 over negative 1, evaluated from 1 to 2. So that would be a 1 over x, evaluated from 1 to 2. So I have 1/2 minus 1. So we get a negative 1/2. Which, that's fine. We can get a negative answer. It just means that more of the curve was below the x-axis, or all of the curve was below the x-axis. Okay. Integral of secant squared is? Think, what's derivative gives us secant squared? Tangent. Remember how we were talking about checking these yesterday, was thinking, okay, if I did the derivative of that answer, I should get back the integrand. So I have tangent pi over 4, yep. So tangent of pi over 4 is 1 minus 0, so 1.
To check that on the calculator.
Right, so let's say you wanted to check this on your calculator. If you go math, 8 is derivative, 9 is integral. Bless you. So let's say I wanted to check this one here. You just kind of type it in, 1 to 2, negative x to the negative 2. And then remember, we just have to put the dx at the end. We did do this, right? I feel like we did. And we got negative 0.5.
Wait, how do you get the integral?
Math, 9.
Yeah.
And then you just type it in. Okay. One more thing, really. We really don't do too much on the mean value theorem for integrals, but average value we do. Now, we did average value before. Remember doing average, like average velocity? Remember how we found average velocity?
Yes.
So before, if you had if you had position, then your average velocity would be what? It would, let's say it's on the integral from A to B. So it would be the displacement over the time integral, right? So think of, what if we were working backwards, right? So in other words, instead of having position, what if I gave you the velocity function and I said, now find the average velocity? We integrate that, okay? Because we would want to find that. In other words, if I were saying from A to B of V of t, I'm kind of jumping ahead a little bit, but I know that hopefully you guys remember all of this stuff with velocity. No, you just had a final. So it would be the position evaluated from A to B. That would give us the displacement. If I want the average, I would divide this over B minus A. So I'd get S of B minus S of A all over B minus A. So, no, is that too confusing? Sorry.
Yeah.
Okay, average value is used when you want to find the average of the actual function. So if I said your velocity was equal to something, and I said, well, what's the average velocity over that certain time interval? This is where this formula comes in. Right, so when I say this, I mean this is an average y value. Like if I give you a curve, and it doesn't matter what it is. Like if I say, oh, here's some curve, and I want to find from -3 to 5. What's the average value on that curve? The way we do that is we integrate, and then we basically either divide by the length of the interval or multiply by 1 over the difference, which is the same thing. Okay. So don't worry about all this other stuff if that was confusing with velocity and average. We'll actually address that later on. So don't worry. But finding the average value of just like a parabola here. Okay, so the average value of f is going to be 1 over, well, this is a and this is b, so 3 minus 0. The integral from 0 to 3 of that function. So I'm finding the average value. So I have 1/3 and then what? Now we want to integrate. Now remember, as soon as you integrate, you don't have to write that squiggly line S anymore. Okay, that's where we're going to evaluate. So what happens when I integrate? I get 4x minus x cubed over 3. And brackets can take the place of our evaluation sign. So I'm going to put the 0 at the bottom right, the 3 at the top right.
Can you put parentheses and then the evaluation?
You could use parentheses and then the evaluation, but whenever you show an evaluation, it should be a straight line. So whether you choose to put parentheses around the whole thing and then just the line for evaluating, or this. So on the AP, you want to just make sure that they are going to pay attention to the notation. So show somewhere that you're evaluating that. Now the 1/3, we can multiply that all at the end. So I'm just going to leave that. So I'm going to first plug in the 3. Remember, we're always going to plug in the top number first, the bottom number second. So I have 4 times 3 minus 3 cubed over 3. Fortunately for us, when you plug in 0, it's just all 0. So I just really have to evaluate that. Good. So we have 12 minus, well, 27 over 3 is 9. So 12 minus 9 is 3. 1/3 of 3 is 1. So our average value is equal to 1. Now, next thing we want to do is figure out at what point in the interval does it assume that average value. So there's two parts to this question. First, we found the average value. Now we want to find at what, think of 4 minus x squared, right? So we're saying from the integral from 1 to 3, we're really looking at like from here to here. So we found out the average value that the function takes on is 1. Now we want to figure out what x value is it going to be. So we want to find a number between 0 and 3. So we take 1. We're going to set the average value equal to our original. So we set 1 equal to 4 minus x squared and basically solve. So we get x squared equals 3. So x would be positive or negative root 3. However, the domain we need to consider, so it has to be in the interval, therefore it's just going to be positive root 3. Okay, that's it. So the last thing is just, we're not going to do anything really with this theorem. It's basically saying the mean value theorem, if you have a function and it's continuous on an interval, right, at some point it's got to reach that average value. It's kind of like we did this with just the mean value theorem. Like if a car starts from 0 and it goes to 60 miles per hour, at some point it's got to be 30 miles per hour, right? It can't skip over that value. It's the same idea. That wasn't so bad, was it? Oh, it was kind of fun, wasn't it?